Welcome back to Statistics. As we mentioned before, some of the most interesting and important problems in statistics, in science, and in life in general are about relationships. We've talked a little bit about how we can visualize the relationship between two quantitative variables using a scatter plot. And we've talked about some of the properties of those relationships, things like whether they're linear or not, what kind of direction do they have, and how strong the relationship might be. But now we want to get into the problem of actually sort of quantifying the relationship. And we do that for two quantitative variables using a technique called linear regression. This is one of the oldest techniques in statistics and it dates back to the 19th century, but it's also one of the most used techniques. And so it allows us to find a trend line that describes the relationship between two variables that are linearly associated. It turns out that computing the trend line can be done by knowing the sample statistics of the explanatory and response variables, as well as the correlation between those two variables. So let's check out the details. The least squares trend line. As I said, this is a way of modeling a linear association. And by that, I mean we want to find a sort of mathematical tool that allows us to discuss and work with the association quantitatively. So here you see the relationship between the dominant hand performance and the performance of the other hand among 40 students in a recent statistics class of mine. We've seen this data before. And the least squares trend line is going to model the positive linear association that we see in the data. Here's a graph of that least squares trend line. Like any line, it'll have an equation, which is here. Notice that we use a special notation for the equation of a least squares trend line. That is, the dependent variable, the response variable, is denoted by y hat. We can use the equation of the trend line to predict the mean response given a value of the explanatory variable. What I mean by that is like consider a specific value of the explanatory variable, which in this case is the dominant hand performance. Think about someone, for instance, who could make 90 hash marks in 30 seconds using their dominant hand. If you look at the graph, there's a range of possible values for the other hand performance, and just kind of eyeballing it, it looks like that range would extend somewhere from about maybe 50 up to maybe 80 or so. What the trend line does is models the mean response that we would see if we could observe essentially the whole population. Think about maybe all students who've ever taken my statistics courses. If we had all that data in our scatter plot, what would be the mean response among all the students who actually scored a 90 for their dominant hand performance? That's what's modeled by the least squares trend line, that mean response. To find it, graphically, we would just go up to the graph to the point on the line corresponding to x equal 90. There you see that point. And to find its y coordinate, which would be the mean response, we go over to the y-axis. And we find that that mean response for x equal 90 is just about 69.5, 69.4817 to be precise. Mathematically, you find that mean response by simply plugging in x equal 90 to the equation of the least squares regression line. Now, that mean response of 69.4817 is our estimate for the population mean. Like any estimate, it would have a confidence interval associated with it. And what you see in this slide is the so-called confidence bands associated with 95% confidence. So for every x value, the associated mean response would come with a confidence interval, and those confidence bands just outline the upper and lower bounds of the confidence interval for each possible x value. For x equal 90, it looks like, and again, I'm just kind of eyeballing the graph, our 95% confidence interval for the mean would go from, it looks like maybe 58 or so, up to maybe a little bit, maybe 70 or something like that. Maybe actually a little bit more than 70, maybe 75 or something. So the least squares regression technique actually gives us quite a bit of information. Probably the first question to answer at this point is, how do we actually find the equation of the least squares regression line? Well, as I mentioned earlier, that's related to the sample statistics of the x and y data and the correlation between the x and y data. The slope of the least squares regression line is given by this formula. We denote the slope by b, and it's the correlation coefficient r times the standard deviation of the response data, of the y data, divided by the standard deviation of the x data, the explanatory data. The y-intercept of the regression line is denoted by a, and it's the mean of the response variable, so y bar, minus the slope times the mean of the explanatory data, x bar. So y bar minus b times x bar gives us the y-intercept of the regression line. And once you have those two constants, you can form the equation of the regression line, y hat equals a plus bx. So for example, for this data that we've just looked at, and there were 40 data points in it, the little table there just shows you the first few of them. But you would take all that data and you would extract the sample statistics. And those are what's shown in this table. So for both the dominant hand and the other hand, for both our x and y data, we would calculate the means, the standard deviations, and the correlation between the two data sets. And then we would apply those two equations to find our least squares slope and intercept. And here you see that worked out. So the least squares slope turns out to be 0.6898, and the least squares intercept turns out to be 3.3997. And that gives us the equation of the least squares line. Y hat, our mean response, would be 3.3997 plus 0.6898 times x. Once you have the equation, you make predictions by plugging into it. So for instance, we have the equation for the regression line. What would be the predicted average response for a dominant hand value of 90? Well, 90 would be our x value, and we would plug that into our equation to find y hat. And that again gives us that 69.4817. And again, graphically, that just corresponds to finding the y value on the line that corresponds to the given x value. What do the slope and the intercept mean in a regression line? Well, like any line, the slope b is the rate of change of y with respect to x. So b is the change in the mean response, y hat, corresponding to a unit change in the explanatory variable x. So for instance, in our dominant hand data, b equals 0.6898 means that increasing the dominant hand performance by 1 unit, that would mean increasing x by 1 unit, corresponds to an increase of 0.6898 in the average performance of the other hand. What about the intercept? Well, like any line, the y-intercept is the y value corresponding to the x value of 0. So in a regression line, A, the y-intercept, would be the mean response correspond to the explanatory value x equals 0. Now in our example, a dominant hand performance of x equals 0 is not really realistic. And so the y-intercept of 3.3997 is not particularly meaningful from a practical point of view. We still need it, of course, to get the correct regression line. It just doesn't have a practical interpretation in terms of, dominant hand and other hand performance. Another note about regression is kind of related to that comment. Extrapolation refers to the process of making predictions from x values that are really far outside the range of the actual x data that you have. So if you look at our data again, our x values spanned a range from about 50 to 130. And, thinking about, for instance, the y-intercept, that corresponds to an x value of 0. 0 is very far outside the range of the actual data that we have. And so making a prediction for an x value of 0 would be an extrapolation. And extrapolation is to be avoided. The reason is that when you extrapolate, you're basically assuming that the trend you see for the data that you have would continue unaltered for data that you never have observed. And so extrapolation is untrustworthy for that reason. There's no reason to assume that the trend we see in the data that we have would continue unaltered for data that we don't have. So extrapolation is to be avoided in regression. So there's a little bit more about linear associations and the regression lines that define them or describe them. We'll have more to say about this topic coming up real soon. In the meantime, stay safe, and we'll be back at you shortly.